Welcome to the latest episode of Star Cells and God. My name is Fuz Rana. I'm a biochemist and a Christian apologist, and I'm joined in studio by Hugh Ross, an astronomer, a Christian apologist, and the founder of Reasons to Believe, which is the organization that sponsors this program. Today we're going to be talking about two discoveries that demonstrate the scientific credibility of the Christian faith. Hugh's going to be talking about little red dots. Do they refute the Big Bang? And I'm going to be talking about a new discovery that undermines a key biological evidence for a young Earth, namely the idea of genetic entropy. Well, Hugh, it's good to see you this morning. I'm glad to have a chance to be able to spend time with you
especially
on camera.
with all of our travels. Don't get to see one another as often.
No, we don't, and I always enjoy having this chance to discuss new discoveries with you. So, Hugh, why don't you take it away?
Sure. Well, it's based on this paper, The Rise of Faint Red. Basically, it's about little red dots. And we got a slide here showing us what they mean by these little red dots, recently coined term by astronomers. And they do look like little red dots, right?
They do.
These are images of the beginnings of the formation of galaxies during the cosmic dawn. And the cosmic dawn refers to the first billion years of cosmic history. And that's one of the primary missions of the James Webb Space Telescope. One of the big reasons for building it is it would have the power to actually look at galaxies and the beginnings of galaxies at very great distances, which corresponds to the very early moments of cosmic history. And so this is an example. And what's amazing is the James Webb Space Telescope, even though it's only been up for a little more than 2 years, they've actually done 5 surveys of looking at galaxies and emerging galaxies during the cosmic dawn. And so this team of astronomers they went through these 5 surveys, and they collected a sample of 341 little red dots.
Yeah, wow.
And a definition of a little red dot, it's basically the core of what will become a big galaxy. So it's kind of the initial seed of galaxy formation. And little red dots were controversial when they were first discovered because they said most Big Bang creation models wouldn't anticipate that would you get galaxies, these emerging cores of galaxies, as bright as they appear to be in some of these James Webb images. Now, of course, we need to recognize that James Webb is going to find the bright ones first, so maybe they're not all bright. But now that they've found 341 of these things, they realize they do look exceptionally bright on the assumption that all the light from these really emerging galaxies is coming from stars. And so what this team of astronomers did is they said, let's actually get some good spectra of these little red dots and see if indeed the light is coming from the stars.
So is the spectral data part of the survey as well?
Yes. And so, because that's what the James Webb's able to do, they give you an image, but they also take an infrared spectrum. So they can see both the emission lines and the absorption lines. And this is kind of the big thing about this paper. This is a preprint, by the way, but it's been accepted to the Astrophysical Journal, and I expect it's going to be published within the next few days. But this is the latest version. And what they discovered is that when you look at the spectra, a lot of the spectra show broad emission lines, which means the spectral lines are broad. And if they're broad, that's indicative of what they call an active galactic nucleus. In fact, a lot of galaxies are classified as non-AGN or AGN. So our Milky Way galaxy does not have an active galactic nucleus. All quasars have an active galactic nucleus. And usually an active galactic nucleus is where you've got a supermassive black hole at the center of the galaxy, where that black hole is sucking in lots of gas and dust, asteroids, comets, planets, and stars, and therefore you get a lot of the matter that's being sucked into the black hole just before it gets to the event horizon. It gets efficiently converted into energy. It explains why quasars are the brightest objects in the universe, because a lot of gas is coming into the supermassive black hole, and it gets converted into energy with anywhere from 10 to 42% efficiency. And to put that in context, our sun's nuclear furnace converts matter into energy with 0.07% efficiency. And so these supermassive black holes are the most efficient power engines for converting matter into pure energy, and explains why they're so bright. Well, the fact that they're seeing these broad emission lines indicative that there is an active galactic nucleus, which means an active supermassive black hole sucking matter into the event horizon of the black hole, tells us a good fraction of the light is not coming from stars, but coming from the supermassive black hole. And so, and again, with an emerging galaxy, right now, a lot of the matter in the universe, ordinary matter, has been converted to stars. But in the early universe, during the cosmic dawn, you got a lot of pristine gas that has not yet been converted into stars. So if that gas is being sucked in to a supermassive black hole, it would explain the broad emission lines, but also explains why these objects are as bright as they are. The light is not only coming from stars, it's coming from gas being sucked in to the supermassive black hole. And for 3 of these 341 little red dots, they actually saw a blue shift. Now, a blue shift means that instead of the, object moving away from us, it's moving towards us. Now, we're looking at objects at very high redshift, so to see a blue shift means there's got to be a jet. In other words, it has to be a jet of ultra-dense gas that's kind of focused towards us. And so even though the little red dot is moving away from us at high velocities due to the expansion of the universe, a jet moving at relativistic velocities towards us would explain the blue shift that you see in the absorption line. So the emission lines are broadened, the absorption lines are actually blue shifted. So this is additional evidence that indeed a lot of the light we're seeing from these little red dots is coming from the supermassive black hole. Because the jets, I mean, if you look at M87, which has got a black hole 6.5 billion times the mass of our star, the sun, you see these very powerful jets coming out from it. Well, likewise, in at least 3 of the cases, we're seeing jets, and they comment in their paper, there's probably more jets if we look for them. So that'll be another project for the James Webb Space Telescope to find these jets. And this was encouraging for me personally, because I don't know about you, but on my Facebook and my X pages, I deal with both atheists and young Earth creationists who say that James Webb is proving the Big Bang wrong. These early galaxies are too big and they're too bright. And it's like, well, they're too bright if you're assuming all the light comes from stars. But if you say some of the light is from stars and some of the light is from the supermassive black holes, this is exactly what Big Bang creation models predict. Almost all of them would predict that. Now, the distinction is this, that in order to get black holes that big, sucking in that much gas and dust, you would need the first stars that form in the universe to be high-mass stars. And we had a workshop back in July where we talked about the James Webb Space Telescope, and I gave a talk where I kind of predicted that this would happen, namely that if indeed many of the firstborn stars are hundreds or even thousands of times the mass of our star, the sun, that's a prescription to get rapid formation of supermassive black holes. And indeed, we've already found 3 galaxies in the first billion years of cosmic history. In fact, the first 700 million years of cosmic history, where the black hole is more than 1 billion times the mass of our star, the sun. So that's strong evidence that indeed in the early universe, you got black holes forming quickly and they're big. And that again would fit what these astronomers are saying. Indeed, black hole formation is efficient, but in order to get big black holes forming that early, you need to have lots of high mass stars. The higher the mass of the star, the more likely you're going to get black hole formation. And hey, if you've got, say, a dozen stars that are weighing 500 times the mass of our star, the sun, every one of those stars is going to end up as a black hole, and they're going to end up as a black hole really quickly. Stars that massive burn up in less than 1 million years, and they end their burning time as a black hole. And if they're in a dense cluster, these black holes will start merging together. And you get a bunch of them merging that are that big, you quickly get a black hole that's millions of times the mass of our star, the sun. So this is favoring Big Bang creation models that say, hey, it's Big Bang models that claim that the first stars, not all of them, but some of them, are very much more massive than our star, the sun. This is additional evidence for the Big Bang because today you can't get stars forming more than 100 times the mass of our star, the sun, and it's because of the chemistry. Once you got a whole bunch of elements in the periodic table, you get molecules forming, and those molecules actually prevent big stars from forming. But in the very early universe, according to Big Bang cosmology, the universe begins with only one element, hydrogen.
Yeah.
And after the first 4 minutes of after the beginning of the universe, a quarter of that hydrogen is converted into helium. But in the very early universe, chemistry is quite simple.
Yeah.
You got hydrogen 2, hydrogen 3, and you got helium hydride, helium and a hydrogen atom. So that would sure make passing a chemistry class easy if all you got is 3 molecules to worry about.
Although there wouldn't be anybody there to teach the class or any students if that's all you had was hydrogen and helium. So
True.
Some other problems there, but yeah.
But what astronomers have known literally for decades, in fact, I was taught this when I was in grad school 50 years ago, is that if all you got is hydrogen and helium and a very tiny trace amount of lithium, which is what happens in those first 4 minutes after the Big Bang creation event, there's really no limit on how big the first stars can be. In fact, it's even possible that you could get gas clouds collapsing where the quote star is more than 10,000 times the mass of our star, the sun. And in that case, it doesn't even become a star. It goes straight into becoming a black hole. So you never actually see it. It goes directly into a black hole. Some Big Bang models say, no, we don't expect that will happen, but we'll get stars that are 500, 800 times the mass of our star, the sun, maybe even 2,000 or 3,000 times the mass of our star, the sun. And so as a chemist, I think this is interesting for you. It's like, okay, knowing that the early universe, according to the Big Bang, had only hydrogen and helium and a trace amount of lithium, what does that do to the chemistry and the physics of star formation? And that's kind of like a holy grail project for astrophysics. We don't have any laboratory to really work on that. And the James Webb is a telescope powerful enough to actually see. We actually have found a gas cloud on the halo of one of these little red dots, and it measured to have only hydrogen and helium. So it actually proves to us that the Big Bang got it right. The universe starts off with only hydrogen and helium. We've actually seen a gas cloud that's got nothing else, which tells us there really is a possibility you could get really big stars. But that's kind of one of the things we want to understand. What is the range of stars that can form in terms of mass? How many of them form? How quickly do they form? What are the sizes of the star clusters? Those are questions that we're hoping that James Webb will answer. We don't have those answers yet, but there's a whole family of Big Bang creation models that predicts a spectrum. Some Big Bang creation models say the biggest stars will be 200 times the mass of our star, the sun, and nothing bigger. Others say, oh no, we can go from 200 to 1,000. Others say we can go from 200 to 5,000. One of them says we can even go up to 20, 30, 40,000. So we're trying to determine which of those models is correct. We're not going to be able to see the individual stars. Right. James Webb is not. A lot of people think James Webb can image individual stars in the cosmic dawn. That's not true. Yeah. It's not powerful enough to do that. But it is powerful enough to see these little red dots, powerful enough to determine the characteristics of the black holes and the centers of those little red dots. And we get enough detailed information on those black holes, it'll tell us which stars form first, what are the mass ranges, when do they form. Some models say they can form as early as 150 million years after the cosmic creation event. Some say 200, some say 250. We want to get that answer. And again, we can't observe the stars directly, but we can observe the supermassive black holes. And so I think this paper is basically saying, let's go after these supermassive black holes. Let's get a very large database of them, get as much detailed information on them. And if we have that, we can do calculations that we can tell us what's happening with star formation when stars first form in the universe. But the bottom line of all of this is James Webb is giving us a stronger case for what the Bible predicted thousands of years ago. And there's an article on our website where I actually take you through what theologians 1,000 years ago, 800 years ago, in reading through the Old Testament, they actually determined that they determine what we now refer to as 4 fundamental features of Big Bang cosmology. So I know they're actually giving a lot of credit to George Lemaitre for discovering the Big Bang, but the truth is people like Moses and Job, Jeremiah, Isaiah, Zechariah, they were writing about the Big Bang thousands of years before astronomers discovered it. In which case, I'm arguing the fact that we're getting progressively stronger and stronger evidence for the Big Bang creation model is good news for Christianity. It's good news for what the Bible was documenting thousands of years ago. Articles up on their website. They can also go to our YouTube channel and see the talk that I gave last July, because what's exciting to me, I was kind of sticking my neck out making predictions, and this paper basically says, hey, the predictions are correct.
Yeah. Well, you know, a couple of thoughts here. One is, and I don't think I fully appreciated this until some of the initial results from the James Webb Telescope were being released, and there were all these statements made in popular news items, particularly that the Big Bang is in trouble. And, you know, a point that you've made here, but I think it's worth emphasizing for viewers and listeners, is there's not a single Big Bang model, but there's multiple models. And some of those models could be refuted, in a sense, by findings from James Webb, but others are going to gain, you know, more support. So this is actually exciting that we're going to be able to get a better sense for which of the Big Bang models are the most robust in light of the results from James Webb.
Yeah, and also to be clear, if you go through the scientific literature on what James Webb is discovering, you read the papers, none of the authors are saying the Big Bang model is in trouble. What they're saying is that certain models of galaxy formation are in trouble. But those models are all components of different Big Bang. So that's where the debate is. You know, which of our models of early galaxy formation are correct? And some of those models indeed are in trouble. But none of those models have any disturbance of our confidence in the Big Bang model. And I'm glad you mentioned this family thing, because I've run into people who say, hey, the fact that there's this broad spectrum of Big Bang creation models tells us the Big Bang's in trouble. It's like, well, wait a minute, that's not how science works. And if you actually look at the history of Big Bang cosmology, back in the 1920s and 1930s, they said, it looks like the universe has a Big Bang beginning. And then by the 1930s and 40s, they're saying, it looks like it's a hot Big Bang beginning. And then we move into the 50s and 60s, and they were saying, it looks like it's a hot Big Bang beginning where the universe seems to have a flat geometry. And they were saying the flat geometry seems well explained if in addition to ordinary matter, we got dark matter, and then by the year 2000, dark energy. And then they were saying, it looks like it's well explained by cold dark matter being much more dominant than warm dark matter. So what you're seeing here is we're going from a very broad description of the Big Bang creation model, where the models become progressively more and more narrowly focused on a subcomponent of that.
And more detailed, it
And
looks
more
like.
detailed. And so that's what's happening. James Webb is going to give us a more detailed Big Bang creation model and a more narrowly defined Big Bang creation model. And that's a sign that you've got a successful model. I mean, if you're doing your research and instead of narrowing in, it's doing this, and you've got a proliferation of competing models and it's getting more and more chaotic and confused, that's a good sign you got the wrong model.
Yeah.
And every scientific model operates that way. We never wind up with just one model.
Right.
I mean, whether you're looking at the chemistry, what's going on with exoplanets, you always have a family of chemical possibilities.
Right.
But as you study it more and more, that family becomes more and more narrowly focused.
Yeah.
If it doesn't, you got the wrong model.
Yeah. Something else that I think bears some discussion, and hopefully this will dovetail with what I want to talk about. But it's interesting because you're making the point, and I would very much agree with you that when you look at what Scripture teaches, it's not just Genesis 1:1, but it's other places in Scripture. You have this biblical cosmology that emerges that looks very much like modern-day cosmology, including the idea that the universe has a beginning, which is really the heart of Big Bang
And
cosmology.
not just a beginning, a space-time beginning, which really separates it
Right.
out from other.
Yeah, I mean, it's remarkable when you read, for example, the Apostle Paul. I think it's in Titus, is it maybe 1 Timothy, where he's making mention about time before time began. That's
Right.
absolutely remarkable, in terms of its the biblical correspondence to the space-time theorems. I always found it odd that young Earth creationists were so much in opposition to the Big Bang, because here you have scientific validation of the heart of biblical cosmology, that there is a creator that brought everything into existence out of nothing, right? Or that, I think it's Psalm 33, God spoke the creation into existence. What would it look like? I've always found that odd that young Earth creationists would run away from what seems to be,
Well,
the
it bothers
most...
me, Fuzz, because they keep saying, why are you at reasons to believe holding on to an atheistic model? It's like, wait a minute. Big Bang cosmology was never atheistic. In fact, if you look at the early history that I document in The Fingerprint of God, it was atheist astronomers that said, we got to get rid of this Big Bang.
Yeah.
It's got a beginning. It implies a beginner. They recognize the biblical implications.
Yeah.
And so they're saying, but the evidence becoming so strong, they're now forced to consider. Yeah. And I remember dealing with a few young Earth creationists say, well, show me a paper where it says that, your observations are proving that God, the God of the Bible, did all this. I said, you won't find papers like that, but you will find papers referring to an agent beyond space and time who's doing miracles to achieve his ends in the universe that he has set up. And so it doesn't use the word God. It kind of reminds me what happened when I spoke at NASA in Houston years ago, where they said, we won't let you use the word God. And I says, well, can I talk about the causal agent beyond space and time that created the universe and designed it so that we humans can exist in it? I said, yeah, you can do that. And that's kind of what you see in the scientific literature.
Yeah.
So the fact that they don't use the word God doesn't mean that it's not implied by Big Bang cosmology.
Yeah.
But yeah, it mystifies me. It's like, why are you rejecting?
Yeah.
This is the ally of the Christian faith.
Yeah.
I think the primary reason they reject it, Big Bang means that the universe can't be thousands of years old.
Right.
And I found it amusing that atheists in the 20th century rejected the Big Bang because it made it too young. They wanted the universe to be quintillions of years old or quadrillions of years old.
Yeah.
Big Bang told us it was only billions. Then young Earth creationists rejected because it's too old.
Yeah.
So it's like, well, atheists and young Earth creationists have one thing in common. They both don't like the Big Bang.
Now, how would you respond to this assertion that just because the universe is a Big Bang universe doesn't mean that it necessarily has a beginning? That I'm beginning to see this challenge coming from primarily atheistic quarters. How would you respond to that?
Well, my response is 100% of the experimental observational evidence tells us that the universe has a beginning. And it's true, we can't rule out the possibility that there is no beginning, because that would mean we would have to be able to observe cosmic history all the way back to the beginning of time. And the closest we can get to the beginning of time is 100 billionth of a trillionth of a trillionth of a second.
Right.
To me, that's quite remarkable that we can get that close. And as we go that close, all the evidence says it has a beginning. But I have run into atheist astrophysicists say, well, maybe something weird's going on in the quantum gravity era. And they're confident that observations will never penetrate the quantum gravity era. But 2 years ago, in observations of gamma ray sources, basically revealed the energy conditions that were 8 times greater than the Planck energy. Planck energy is a technical term for the energy you encounter when quantum mechanics conceivably exert more force than gravity and the dynamics of the universe. And they said, well, if we're earlier than 10 to the minus 43 seconds, maybe we got exotic physics that we can't test or measure that would enable us to find a loophole around the space-time theorems. In fact, an atheist astrophysicist at, he's no longer at Caltech, but was, Sean Carroll, he authored what was called the quantum eternity theorem. But his quantum eternity theorem was assuming that space-time fluctuations when the universe is younger than 10 to the minus 43 seconds would be so large that it would be possible to get a loophole around the space-time theorems. Well, we now penetrated the quantum gravity era by a factor of 8, and that penetration shows us those non-theistic models that avoid a beginning don't work. Now, what's happened is the atheists say, well, we'll just retreat. But this is what I notice. People who are claiming there's no beginning to the universe, they're on a continual retreat, being pushed back into a smaller and smaller corner of speculative space to defend their idea there is no beginning. And if you're always on the retreat, and if your retreat is rapid, that's a sign you got the wrong model.
Yeah.
So, but will we ever be able to absolutely prove that there's a beginning to the universe? No. That would require us knowing absolutely everything about the universe back to time equals 0. And that would require instruments with the capability of being able to probe with infinite energy. So that's not going to be funded anytime soon. So, but I use the analogy. Even though I've been married to my wife for 47 years, I still lack absolute proof that she exists. All I got is a high probability. But with every year we're married, the probability goes up. And I have no rational basis for denying her existence. Likewise, there's zero rational basis for denying that the universe has a beginning. I can't think of anything that's more observationally, experimentally established than the fact that the universe has a beginning. The Bible got it right.
And that's a really powerful point. So,
well, tell us about these this genetic entropy.
I sure will. Well, and to maybe ease us into the transition and give the viewers and the listeners a break. You know, it's interesting because in the English language, sometimes words can be misleading, right? Or they imply something that isn't necessarily true. So, for example, a firefly isn't a fly, it's a beetle, right? A silkworm isn't a worm, it's a caterpillar. pencils don't have lead in them. They have graphite,
Yeah.
right? It's carbon. And a peanut isn't a nut, it's a legume, right?
Yes.
Right. And for our purposes, in Genesis 1, a day isn't a normal day or a calendar day. It's actually a period of time. And, and you've done, a masterful job in a number of your books, A Matter of Days, for example, where you show, that that the best understanding of the word yom in Genesis 1 is a period of time or an epoch.
For the creation days.
Yes, for the creation days. That when you look at some of the clues in Genesis 1, but more importantly, look at other creation accounts and you integrate them, the best reading is really something other than a calendar day. That it's really a period of time, and this is actually significant because there's this perception that exists both in the church and outside the church that a simple reading of Genesis 1 indicates that God created over a period of 6 successive 24-hour periods of time, and that when you then look at the genealogies in Genesis 5 and 11 and you misuse them by trying to calculate when Adam and Eve were created, you wind up with an age for humanity at about 6,000 years, and by implication, the age of the earth and the age of the universe at about 6,000 years. And for many young people growing up in the church, this, of course, is deeply problematic because it sets Genesis 1 to be in direct opposition to the overwhelming evidence that we see.
Including these little red dots we're talking about.
Including the little red dots, for a universe that's approximately 13.8 billion years, an Earth that's 4.5 billion years. It's remarkable to me, but, life has been present on the Earth for easily 4 billion years. And, humanity appears in the neighborhood of 100 to 150,000 years. This is all highly well-established science that's, in my mind, impossible to refute or impossible to ignore. You debated Terry Mortensen last fall at Southern Evangelical Seminary's Steadfast Conference. Right. And a point that you made, I thought, was really powerful, that the antiquity of the universe, the antiquity of the earth, the antiquity of life is not a scientific debate. How you read Genesis 1 is a biblical debate or a theological debate or an interpretive debate.
There is no scientific debate.
There is no scientific debate. And so that's really very significant. But, the fact that, again, young people in the church who have any kind of scientific savvy recognize this, and when they're told that the earth is young, their option is to walk away from their faith, or one of their options. And there are many people that are atheists or skeptics that seemingly think that the Bible is incompatible with the antiquity of the universe and the earth and life, and so therefore reject the Christian faith and most importantly the gospel. And so, it's really important, to communicate to people that there is very powerful biblical reasons to think that indeed day is a period of time. But for those young earth creationists, those people that are committed to a young earth, in light of this scientific evidence, they respond by trying to marshal a scientific case for a young earth. And it's interesting to me because, as you well know, a lot of the so-called evidence comes from astronomy or geology, and you've done a great job in A Matter of Days and other places really responding to these claims. But it's interesting because I'm seeing more and more biological arguments for a young earth emerging. And one of them has to do with soft tissue remnants and fossil remains, which we responded to in Dinosaur Blood and the Age of the Earth. But that leads me to what I want to talk about today, which is the concept of genetic entropy, which is another biological argument for a young Earth. And
John Sanford, I think, is the one
John
that's been
Sanford.
promoting
And
that.
we actually, a number of years ago, had him
He was here.
at our
Yeah,
offices.
right.
Really fine Christian gentleman. And when I was working on the manuscript for my next book, Should We Play God, I talk about genetic modification of plants, GMOs. And John Sanford plays critically in that, believe it or not. He was one of the co-inventors of something called the gene gun, which is a technique used in genetically engineering plants. So he's not a slouch when it comes to science. He's a very fine Christian gentleman, but he is a young earth creationist. And part of the reason for that is his concept of genetic entropy. And when I first heard his arguments, I thought, wow, this is interesting. He seems to have a strong case here, but it just troubled me. I couldn't quite accept it. And I'll explain what the argument is and why that was the case. But to understand the argument, we need to understand the fact that there are different types of mutations, right? That genomes undergo mutational change. And there are three types of mutations: beneficial, neutral, and deleterious. And
Right.
by far, the most common mutation is a neutral mutation, where you're changing the genetic code, but it really is not, it's not having any kind of impact on gene expression or the structure of proteins. And again, most mutations are neutral. Very few are beneficial. People try to quantify the ratios. I don't know if those ratios that people present are valid, but when you look in the literature, almost everybody agrees beneficial mutations are relatively rare. More commonplace, if those mutations impact the organism, they're going to be deleterious, meaning they're going to cause harm. And that
Right.
makes sense because biological systems are highly optimized. And so anything you do to change that system is going to drive you away from the optimum.
Right.
It's
right.
just, math. And there are two types of deleterious mutations. One are extremely harmful. Those tend to be eliminated by natural selection right away. And the reason is that if it's a really harmful mutation, the organism that
It's not going to reproduce.
it's not going to reproduce or live.
Yeah.
Maybe not live, or if it does live, it's not going to reproduce. And if it does, that mutation is just going to be cleaned out of the genetic population, or the population by natural selection. What is problematic, and evolutionary biologists will acknowledge this, are what are called mildly deleterious mutations. These are mutations that undermine the fitness of the organism, but the organism is still able to reproduce and survive. But over time, these mildly deleterious mutations will not be cleaned out because of natural selection, will actually accrue in the genome of organisms in that population. And the idea is that once you reach a tipping point, that population will go to extinction. And so this is the argument that John Sanford makes, where he talks about the accumulation of these mildly deleterious mutations as being genetic entropy. And in an article that I pulled off of the ICR website, Institute of Creation Research, a young earth organization, an article by Jeffrey Tompkins, who is a geneticist, a young earth guy, he said that one of the most important finds in recent years came from modeling the accumulation of mutations in the human genome over time using computer simulations. And here he's referring to John Sanford's work.
Right.
Researchers found that this buildup of mutations can only reach a certain level before the genome completely deteriorates and humans go extinct. The process of degradation, called genetic entropy, fits perfectly with a recent creation of 6,000 to 10,000 years ago. So in these modeling studies, John Sanford basically reports that this genetic entropy executes its full effect at about 3,000 to 4,000 years ago. So the argument would be, look, the only way that you could have humanity and all these animals that are present on the earth is if it's a recent creation, that animals are not going to populations of distinct species are not going to be able to survive.
Well, I do remember when John Sanford was here, he said, 6,000, but I can do the same modeling and take it out to 1 million years or anything in between. He was basically saying, I don't think you can push it out 1 billion years for something as complex as humans, but there is this range.
Yeah.
He says, I think the best spot is 6 to 10,000 years ago.
Well, and that's the thing is when you do computer modeling, you're making certain assumptions,
Right.
and you can make assumptions.
I just wanted to be fair to him. He did indicate, hey,
Yeah.
these are the assumptions.
Right.
This is why I come to this conclusion.
Now, but I've always been troubled by this as a young Earth argument because when you look at life's history, it's very clear that there are species that have existed for
a long time.
hundreds of thousands, millions, hundreds of millions of years in some instances. So this can't be a valid argument, but yet it's very difficult to refute the reasoning. It's not an outlandish argument. I've even seen some old Earth creationists embrace Sanford's ideas because they argue, well, this is a direct challenge to this notion that natural selection can drive evolutionary advance. And I've still been uncomfortable with that because I'm not completely comfortable with genetic entropy. Well, along comes this paper published fairly recently by a team from France. This has actually been published as a
is it a preprint right now?
Yeah, as a preprint. Oops, there we go.
There we go.
As a preprint, it's available at the PLOS genetics site as an uncorrected proof, but it's been peer reviewed. It's once the manuscript is cleaned up, it's going to appear in the journal. And what they're doing in this study is they're trying.
So it means it's been accepted for publication.
Yes.
Yeah.
So what these researchers are doing is they're trying to quantify the different types of beneficial mutations. When we talk about beneficial mutations, there are different types of beneficial mutations that these researchers have identified. And again, they've quantified them. And when you take these into account, it actually completely unravels the whole genetic entropy argument, not only as evidence for a young Earth, but as, frankly, a challenge even to evolutionary innovation. And they identify 3 types. The first is called an adaptive beneficial mutation. And this typically happens when the population undergoes a change in the environment. Organisms are highly adapted to a particular environmental setting. They're optimized for that setting. And if that setting changes, the technical term is the fitness landscape becomes unstable. What happens is there are mutations that are happening, and some of those may very well help that organism respond to the new environmental setting. And if that's the case, and if it's beneficial, of course, then it'll take hold in the population, and it's called adaptive. It's a beneficial mutation that helps the organism adapt to the new fitness landscape. If the fitness landscape is stable, if the environment is stable, there are other mutations that can take place that offset the effects of deleterious mutations. One of them is called a compensatory mutation. In other words, it's a mutation that happens elsewhere in the genome that alters the organism, and it compensates for the loss.
Deleterious.
The deleterious mutation. It offsets it. And these are actually considered to be innovative. So that even in a stable fitness environment, the organism, according to this model, can actually innovate, right? And then the last one, which is what really is of importance and what this research team studied, are called non-adaptive beneficial mutations. And what they show here is that somewhere between 15 to 40% of mutations that are beneficial in a survey of 87 mammalian genomes are non-adaptive, meaning that the organism is in a stable fitness regime where the environment is not changing. And when a deleterious mutation happens, there is a mutation that can take place that reverts the genome back to the original state, right? And this is not hard to understand because some mutations are called transitions, where an A goes to a G or a C to a T. And these are very easy mutations to take place. These are called transitions, and they're easy to reverse.
Right.
There are mutational hotspots in genomes, right? And so there's only a limited number of ways that different loci can change. And if it's a hotspot, then the mutation could revert. So they're saying a substantial fraction of mutations in a stable fitness landscape are actually non-adaptive, reverting the organism back to the original state. Well, this now means that, for a population of organisms, yes, indeed, mildly deleterious mutations are accumulating, but they're being constantly offset by compensatory mutations as well as by
Reverting ones.
These non-adaptive ones. Yeah. And so this is what the writers of the authors of the paper say, and that is, our work confirms that deleterious mutations substitutions are accumulating in mammals and are being reverted, generating a balance in which genomes are decayed and restored simultaneously at different loci. So this, again, completely unravels the genetic entropy argument for a young Earth. The reason why organisms can survive well beyond, as a population, well beyond 3,000 or 6,000 years is because of these balancing effects, deleterious mutations and not adaptive beneficial mutations. It also means that you can't really use genetic entropy as a challenge to biological evolution. There's other challenges that I think are legitimate complaints. This isn't one of them. Now, to put this more in terms of a positive case for the Christian faith, because I think there's actually a design feature in this work that emerges. You and I are old Earth creationists, so we don't ascribe to an evolutionary history to life. But it doesn't mean that we reject every aspect of the evolutionary paradigm. Clearly, microevolution, variation happening within a species, and speciation takes place. And the mechanisms that drive these microevolutionary changes, speciation, are essentially, accumulation of mutations operated on by natural selection. The very mechanisms these researchers are pursuing. Well, think about this. If you've got an organism that is living in a world where mutations are taking place, and it's also a world where things are ever changing.
The environment's changing.
There needs to be a way for that organism to respond to the environment, and mutational changes allow an organism to adapt to new environments. And it also says that, yes, indeed, most mutations are going to be harmful. Again, if you take a design perspective, that makes sense because organisms are highly optimized. But what is offsetting those deleterious mutations are other mutations that are either compensating or are reverting to the original state. So you could see this as a design feature, as part of God's providential care.
I can even quote a Bible verse. God created these species of life to reproduce after their own kind. In order for a new life form to reproduce after its own kind, it needs to be able to adapt to changes in the environment. So I can see God saying, okay, let's design the genomes so that this adaptability can occur, so they really can reproduce after their own kind.
Yeah.
So this all makes sense.
Yeah. So, the bottom line here is this genetic entropy argument. It's a very interesting argument. There is a technical rigor to it, to be fair, but I don't think it withstands, it's not withstanding ongoing scientific scrutiny.
Well, it's an example where you can make what looks like a really good argument if you only look at one side of the equation. What these researchers have done is say, well, let's actually look at what's happening on both sides. Now, I'd like to see, I presume that they end their paper by saying there's a lot more that could be done here. It's like, wouldn't it be interesting to actually see, okay, how frequently do these reversion mutations occur? Where do they occur? And then also, okay, these compensation mutations. Let's get some statistics on this.
Right.
I mean, is it a perfect balance between the deleterious and the reversion of the deleterious, or is there a slight imbalance?
Right.
These are interesting questions.
Right.
And could shed a lot more light on the creation-evolution debate.
Right.
But
Yeah.
that's for the future.
Yeah. But, you know, at least for our purposes at this point, you know, the larger point is that, you know, as you mentioned, I've yet to see a young Earth argument from a scientific perspective that has withstood scientific scrutiny.
Right.
Right. It's either an incomplete presentation of the science, or or future scientific discoveries expose the flaws in the argument. So, you know, all this to say is that, given that there isn't a scientific case for a young Earth, and that a more robust biblical case can be made that, you know, days are a period of time, which then allows this beautiful harmony between the Genesis 1 account and the history of the Earth and the history of life on Earth. Why would you know, want to advance a young Earth perspective? You know, it's very similar again to the point we discussed earlier.
You started off by talking about integration. And, you know, what this paper has done is say, okay, we do have these mildly deleterious mutations, but we also see things happening at genetic level that can reverse these mildly deleterious or compensate for them. You're looking at, you know, the whole picture. Likewise, when it comes to the Bible, you can't just look at Genesis. Let's look at all the content in the Bible that pertains to creation. So I think this is it's actually a biblical principle. You see it in the Proverbs. An argument sounds good if you only look at one side, but then another man gets to speak. I think it's in Proverbs 18, it says that. Basically, the Bible is telling us, look at both sides before you come to a decision. Or if there's three sides, look at all three sides.
Yeah.
And I think that principle applies scientifically and biblically.
Yeah, yeah. All right, Hugh. Well, I think we've exhausted the topic for the day. So
this is fun, Fuz.
yeah. Thanks, Hugh. And thank you for joining us today on Star Cells and God. We'd love for you to join the discussion in the comments below. Remember to like the video and to subscribe for more content. New episodes of Star Cells and God release every Wednesday and are available here on our YouTube channel and on your favorite podcast app. Be sure to share this video with a friend, and remember, the more we know about science, the more we have reasons to believe.